friends, my name is Mudit Khitan. I am a professor of computer science at Jaipur National University. I am going to teach you about number systems in computers. So why we are going to talk about numbers when we are talking about computers? A computer system is based upon numbers. Every calculation in a computer system is based upon numbers. In fact, the very basis of a computer system are numbers. And you should be surprised and convinced to know that the decimal number system that we use today was developed by an Indian scientist or an Indian sage, Aryabhatta, thousands of years ago. The decimal number system, or also known as the positional number system, is the basis of all the modern mathematics, physics, and computing. So today we are going to talk about decimal number system or the positional number system and how it impacts or affects our computer calculations. Let me start. We can divide our number systems into basically two categories: positional systems and non-positional systems. Positional systems are those in which the position of every digit or every numeral is going to contribute towards the value of the number. For example, if I say 23 in decimal number system, then the position of 3 is units and the position of 2 is tens. It means that 3 contributes 10 raised to power 0 and 2 contributes 10 raised to power 1. This is the value 20 and this is the value 3. So the total is 23. So this is what we mean by positional number systems. In case of non-positional number systems, you must have studied about the Roman numerals. For example, this is 1, this is 2, this is 3, this is 4, this is 5, this is 10, this is 9, this is 11, and so on. In case of a non-positional number system, like a Roman numeral system, it is not possible to carry out mathematical calculations which are beyond simple addition and subtraction. It is not even possible to carry out multiplication and division without much complexity. So, Roman number systems were only good as far as the basic transactions or basic recording of transactions was concerned. But when it came to faster calculations, they were completely lacking in any kind of rigor. So we take to the positional number system or the decimal number system we have seen. So in your primary classes, you must have studied about that these are the positions of the number system. So we have seen that before the decimal place, there is the unit place, the tens place, the hundreds place, the thousands place, the 10,000 place, and so on. So these are the positions. And whenever we are talking about positions, the contribution of that number is actually a contribution which is the value of the digit multiplied by the power of 10. So here the power of 10 is 0, the power of 10 is 1, the power of 10 is 2, the power of 10 is 3, the power of 10 is 4. Or 10 raised to power 0 is 1, 10 raised to power 1 is 10, 10 squared is 100, 10 cubed is 1000, and 10 raised to power 4 is 10,000, and so on. So you can see that the positions are increasing from right to left. This particular digit or the digit at the unit place is also known as the least significant digit. And a digit on the rightmost side or the leftmost side is actually called the MSD, not MS Dhoni, but the most significant digit. Now this is a basic concept which we have to remember, and based upon this particular concept, we are going to study about different number systems which are very helpful and useful as far as computer sciences are concerned. Using the same concept of positional number systems that we have just now studied in decimal number systems, we can also make other number systems such as a binary number system or an octal number system or a hexadecimal number system. So what is binary number system? Binary number system stands for 2. Octal stands for 8 and hexadecimal stands for 16. If you see decimal or the deca in the decimal number system stands for 10. 10 means there are 10 different digits from 0 to 9. The first digit is not 1, the first digit is 0, and the highest digit or the largest digit in decimal number system is 9. Similarly, in a binary number system, the digits will be 2, only 0 and 1. The least digit is 0 and the highest digit is only 1. In case of octal decimal number system, where the base is 8, the least digit is going to be 0 and the highest digit is going to be 7. And in case of hexadecimal number system, well, because we are short on digits, we are going to talk about hexadecimal number systems later. But for now, you can maintain that the least digit is 0 and the largest digit is F, which is representative of 15. So we are going to leave the octal and hexadecimal number systems for now, and we are going to concentrate on binary number system on the basis of the concepts which we have studied for the decimal number system. In case of binary number system, 2 is also known as the base, just like 10 is called the base of the decimal number system. Just as 10 has a very special place in case of the decimal number system, 2 is also going to have a special place. Whenever we want to store anything in a computer system, it is always the simplest form to store that is in the form of binary signals. Because computer system is an electronic machine, it can understand 2 different states of an electronic pulse. A higher current or a higher charge can be treated as a value of 1, and a lower current or a lower charge can be treated as a value of 0. So, it is easy for a computer system to differentiate between 2 different states of a current or a charge, and it can attribute the values 0 and 1 to them. So whenever I want to convert any numeric value which is written in decimal number system to a binary number value, I simply have to divide that value by base 2. Let's say I want to convert value 255 to binary. The simple process is a division process which we are going to carry out. So the question is, the value 255 in decimal is equivalent to what in binary? So let's carry out. The division process is quite simple. You have to divide the given number in decimal number system by 2, and you have to take the quotient as the new divisor and the remainder, which is going to be either 0 or 1, on the right hand side of the division table. So when 255 is divided by 2, the answer is 127. The quotient is 127, and because 2 does not divide 255, there is a remainder which is 1. So we are again going to divide 127, the new quotient, by 2, and we are going to continue the process until we get a 0 in the quotient. So let's carry out this process. So 127 is divided by 2. So we get 63. And the remainder is 1. We again divide this value by 2 and we get 31, and the remainder is 1. We again divide 31 by 2. I get 15 and remainder is 1. I again divide by 2. I get 7 and remainder is 1. I again divide by 2 and the remainder is 3 and 1. Again a division by 2. I get 1 and 1, because 2 times 1 is 2, which goes into 3. So I get quotient as 1 and remainder is 1. Finally, when I divide this final value, the final quotient of 1 by 2, I get my quotient as 0, because 2 cannot divide into 1, and the remainder is 1. So this is my division, these are my remainders, and now I am going to collect these remainders from downwards. So how many ones are there? 1, 2, 3, 4, 5, 6, 7, 8. So let me write it down here. 1, 2, 3, 4, 5, 6, 7, 8. So I say that 255 in decimal system or 255 with base 10 is equivalent to 11111111 in base 2 or binary. Now, how do I check whether this value is correct or not? Just remember, at the beginning of the lecture, I told you how do we calculate a value of any given number. Remember, I took this example of 23. This number is divided into two parts, or as many digits there are. 3 multiplied by base raised to power 0 and 2 multiplied by base raised to power 1, and these two values are added. Where do I get the 0? Because it is at position of unit. Where do I get this 1? Because it is a position of tens. So, whenever you have any number, the positions move like this, and so on. This is the decimal point, and every digit on the left hand side of the decimal point increases in position like this. The first digit which is adjacent to the decimal point has a position 0, then 1, then 2, and so on. The same rule applies with binary numbers. In this case, we are multiplying with the base raised to power of the position. Here the base is 2, here the base was 10. So we are going to multiply the same values with the power of 2's. Let's see how. So let's take the first one, and we are going to write the positions for easy reference. This is position 0, position 1, position 2, position 3, position 4, position 5, position 6, and position 7. You can see there are 8 positions starting from 0 to 7. So let us multiply all these. So 2 raised to power 0 multiplied by 1 plus 2 raised to power 1 multiplied by 1 plus 2 raised to power 2 multiplied by 1 plus 2 raised to power 3 multiplied by 1 plus 2 raised to power 4 multiplied by 1 plus 2 raised to power 5 multiplied by 1 plus 2 raised to power 6 multiplied by 1, and finally 2 raised to power 7 multiplied by 1. Anything raised to power 0 we know is 1. So 1 into 1 is 1 plus 2 raised to power 1 is 2 multiplied by 1 is 2. 2 square is 4. 2 cube is 8. 2 raised to power 4 is 16. 2 raised to power 5 is 32. 2 raised to power 6 is 64. And 2 raised to power 7 is 128. Let us add all these. 1 plus 2 is 3, plus 4, 7, plus 8, 15, plus 16, 31, plus 32, 63, plus 64, 127, plus 128 is 255 in decimal. So you can see that using this division method, I converted a decimal number into a binary number, and using this multiplicative method, I converted a binary number into a decimal number back. So these two methods are complementary to each other in the sense that whenever you want to find out the binary equivalent of a decimal number, you are going to apply this kind of division method, and whenever you want to find out the decimal equivalent of a given binary value, you are going to apply this kind of multiplicative method. Now let us take one more example to solidify or to concrete the concepts. Now in this particular example, all the digits were 1. The binary value has all the digits as 1. So let us take some other value which has 1s and 0s both, and we are going to get some other answers. Let's see. Let's take a value 101. Now this is a decimal value, and I want to find out the binary equivalent of this particular value. The process is the same. This is a decimal value. Now you can see that it also has digits 1, 0 and 1. Now how do I differentiate whether a given value which is having only the digits 1, 0 and 1, whether it is a binary value or a decimal value? The simple thing is that I apply the base to the value. If nothing is given, you are going to consider it according to context. Most likely it is going to be a decimal value, as you have been using them. But when you talk about computer science, if the context is not given, you are going to assume them to be decimal, otherwise they are going to be binary. So let's find out the binary equivalent of 101 in decimal. When you divide 101 by 2, you get the quotient as 50 and the remainder as 1. Because the quotient is not 0, you again apply the division. And this division, when carried out, it gives you 25 as quotient and 0 as the remainder. You again apply the division, and upon applying the division, you get 12 as quotient and 1 as remainder. You again apply the division, you get 6 as quotient and 0 as the remainder. You again apply the division, you get 3 as quotient and 0 as remainder. You again apply the division, you get 1 as your quotient and 1 as your remainder. And finally, when you apply the division again, you get 0 as your quotient and 1 as your remainder. Remember again that we have to collect the remainders or collect the remainder digits from the bottom. It is a bottom up collection. This is going to be your MSB. In case of decimal numbers, it was MSD, the most significant digit, or the LSD, or the least significant digit. In case of binary number systems, it is going to be the MSB, or the most significant bit, or the LSB, or the least significant bit. So 1100101. 1100101. This is my binary equivalent of 101 in decimal. Now, if I want to verify that whether this particular calculation is correct or not, whether this process is right or wrong, again I have to apply the multiplication process and to get the decimal equivalent of this binary pattern. Positions as usual, position 0, 1, 2, 3, 4, 5 and 6. So there are 7 bits in this particular number or this binary number with the positions 0 to 6. So let's multiply each of one of them. So 1 into 2 raised to power 0 plus 0 into 2 raised to power 1 plus 1 into 2 raised to power 2 plus 0 into 2 raised to power 3 plus 0 into 2 raised to power 4 plus 1 into 2 raised to power 5 and finally 1 into 2 raised to power 6. 2 raised to power 0 is 1, 1 into 1 is 1. Anything multiplied by 0 will be 0. So we do not need to even calculate the powers of 2. We'll simply write 0 over here. This is quite easy. And 1 multiplied by any value is that value. So we do not need to carry out the multiplication by 1 also. We can simply find out the powers of 2 and we can write them down. So 2 raised to power 2 is 4, 2 raised to power 5 is 32 and 2 raised to power 6 is 64. Now let us carry out the addition. 64 plus 32 is 96 plus 4 100 plus 1 101 in decimal. So you can see that 101 or 101 in decimal number system is same as 1100101 in binary number system. And we also just saw the shortcut to convert these values into decimal or binary. This is something which our brain has already grasped, but we are unable to identify it. Let us take another example and carry out this process. Now this time we are not going to carry out elaborate multiplication or division process. We are going to use a shortcut method to convert any decimal value into a binary value and to convert a binary value back to the decimal value. We are going to use the same thing, but instead this time we are going to use some kind of shortcuts. And for those shortcuts, I am going to list out the powers of 2 in their increasing order. How? Let's see. 2 raised to power n and n, or let's say n and 2 raised to power n. So we have n value 0, 1, 2, 3, 4, 5, 6, 7. This much should be sufficient for an example. 2 raised to power 0 is 1, 2 raised to power 1 is 2, 2 raised to power 2 is 4, 2 raised to power 3 is 8. You just need to double the previous value. So this becomes 16, 32, 64 and 128. You don't need to even calculate these values because we are working with the powers of 2. You just need to double the value every time. Now let us use a shortcut method to convert a decimal value into a binary value, and then again use a shortcut method to convert a binary value to a decimal value. Let's take a value, say 137. 137 is an odd number, and odd numbers are very tough to crack. So we have to find out what is the binary equivalent of 137, and we have to do it using a shortcut method. Now 137 is given, and this is the table which is depicting the powers of 2 from 0 to 7. Now identify which is the highest power of 2 that can be subtracted from the given number. I am going to repeat myself. Identify which is the highest power of 2 that can be subtracted from the given number. Your given number is 137. Can you subtract 128 from 137? Yes, you can. Let's write 2 more powers over here to make things more interesting. Okay. So you have 137. Can you subtract, can you subtract 2 raised to power 10 or 1024 from 137? No, you cannot. Simply speaking, we can go into negative numbers, but we are not going to negative numbers. Can you subtract 512, which is 2 raised to power 9 from 137? No, again not. Can you subtract 256 from 137? No. Can you subtract 128 from 137? Yes. So this is the first bit we have in our control. So let's mark 1 for that. Now in the rough part, or in the part of your brain where you do some kind of rough calculations, just find out the subtraction of these values. 137 minus 128. The answer is 9. And this is the position 7, because this was the value which you subtracted from 137. So mark the position 7. This is the most significant bit of your binary number. And all the other positions, any position before that are always going to be 0. And other positions beyond that, which is the position 6, 5, 4, 3, 2, 1 and 0. These are the positions which we need to fill now. Now this is your new solution or new answer. Now find out the highest power of 2 which you can subtract from 9. We can see that 8 can be subtracted easily from 9 but not 16. So 2 raised to power 3 or 8 can be subtracted easily from 9. So how do we do that? This is 2 raised to power 3. So I put a 1 over here and I subtract 8 from this value. So I get 1. Now this is my new solution, or this is my new remainder. I again find out the highest value of 2 that can be subtracted from this new remainder. So this is 2 raised to power 0 or 1. So I put a 1 over here. So 1 minus 1 is 0. My subtraction is over. It is done. Okay. Now what about these blank areas, these blank bits? What do I do? I simply put 0 to them. This is my binary number. You see, you just have to remember this simple and sweet table of powers of 2, and you can compute the binary equivalent of any given decimal number using the shortcut method also. So we have 1 0 0 0 1 0 0 1 equivalent of decimal number. And how do I verify whether this can be correct or not? Again, you have the basic elaborate multiplicative method, or we can use another shortcut method. How do I do that? Identify the positions. The positions are 0, 1, 2, 3, 4, 5, 6, 7. These are the positions. Now remember, in the just concluded example, in the previous example, I told you anything multiplied by 0 is going to be 0. And this you also know that. So 0 multiplied by any raised to 2 raised to power anything is going to be 0. So we just need to skip these positions which represent the zeros. So we are now concerned with only those positions which represent ones. And anything multiplied by 1 is the same number. It means we are concerned with only the final results of the values. So what do you get? 2 raised to power 7, which is 128, plus 2 raised to power 3, which is 8, which is 136, and 2 raised to power 0, 1. So the total is 137. So you can see that using this simple table of powers of 2, you can easily find the decimal and binary equivalents of any given number. This is it for today's lecture, and we are going to meet in another lecture concluding the number system discussion and doing some addition and arithmetic on number systems.